Good. 4.8 Regularization of approximation methods. So far we have learned different techniques how to regularize one single operator. In this section we will learn how to regularize a whole sequence AN. And here's our starting point for this section. What can I do if my projection method AN, you know what projection method means, it's given by A and then you have projections from left and right that both converge to the identity so that AN converges to A, is not applicable. So you've discretized your equation, you have run your code and it's not working, it's not converging, it's doing something stupid. What can you do? And then Polski comes and says, well, non-applicability of your method could have two reasons. Either your operator is not invertible or your sequence is not stable, or possibly both. So it could be because A is not invertible or because AN is not stable. And remember, stability is again defined via two conditions. First condition, all AN with a sufficiently large n are invertible, and second condition, the inverses are uniformly bounded. So again, either of these two could go wrong. So there might be a whole subsequence of non-invertible operators, or there is at least a subsequence of your sequence AN where the inverses grow to infinity. Okay, so let's label our three reasons for non-applicability by 1, 2, and 3. And now let's try to deal with these three problems here one by one. So when your boss is asking, can we fix this? You just answer in a calm voice, yes we can. Just like Bob the Builder or Barack Obama, whichever you prefer. So how do you fix problem 1? A is not invertible. Well, of course you use the pseudo-inverse instead of the inverse, and you solve the least squares problem instead of the equation. And how do you solve problem 2 of non-invertible operators AN in your sequence? Well, you do just the same. So it remains to solve problem 3. But thanks to our last subsections, we are well prepared for this problem also. We know how to limit, how to bound the norm of your inverses. Let's simply apply TSVD regularization with a fixed epsilon to all the operators in my sequence, and that will make sure the norm of the inverses will not exceed 1 over epsilon and thereby be bounded away from infinity. Okay, very nice. So we have found suitable replacements for the operators and the problems. But do they still fit together? Your boss is asking, and that's indeed a very good question. So precisely, we have replaced AX equals B by AX approximately equals B. So the question is, can we approximate this unique solution X of the least squares problem by the unique solutions of these least squares problems? Or maybe we even had to fix step number 3 and apply the TSVD to these ANs. And here we abbreviate the TSVD regularization of AN. Okay, so that's the question. And if the answer is yes, then that's what we usually call applicability of this method or that method to this operator. But obviously this is not the kind of applicability that we used to mean, because now we have least squares problems here and we have this TSVD regularization involved here. So we need completely new versions of what applicability means. We probably even need new stabilities, and we certainly need new Polski theorems. So we better get started. Theorem. Let A be an operator x to y, where x and y are both Hilbert spaces, and let an be a projection method for A. So in particular, an converges strongly to A. And now here comes a new condition. If, in addition, an star converges strongly to A star, then the following holds. Statement A. There exists an n0 such that for all n greater than or equal to n0, the operator an is invertible, and the supremum of the norms of the inverses is bounded. Okay, of course you recognize this is nothing but stability of the sequence an. Now the statement of A is that this stability here is equivalent to invertibility of A and the usual applicability of your method, where we write applicability in this shortest possible form. So it all comes down to the inverses converging strongly to the inverse. And that's statement A, and it feels a little weird because we are used to Polski in a slightly different way. We know that applicability is equivalent to invertibility and stability. So something went wrong here, or well, maybe if we call it a theorem, then it's probably right, but it's different than before. But of course we also have this additional condition, so maybe that makes the difference. Let's discuss this afterwards, and let me continue with statement B. Statement B is almost an exact copy of statement A, only with more Penrose pseudo-inverses in place of inverses. And then you just rename these properties here into more Penrose stable and more Penrose applicable. And this convergence here is very good news because it's telling you that the least square solutions of this problem here, which you get by applying this operator to the right hand side Bn, converge to the least square solution of that problem here, which you get by applying this pseudo-inverse to that right-hand side. But because the pseudo-inverses converge to the pseudo-inverse and the right-hand sides converge to that right-hand side, you will get that these xn's converge to that x. Very good. Well, similarly like you did here with proper equations and solutions. Okay, it's getting even better. We also get something for this situation where we have TSVD regularization involved, and that is point C in our theorem. And now C looks a little bit different than A and B. There exists an epsilon greater than 0 such that the difference between the TSVD with epsilon regularized operator an and the non-regularized operator an goes to 0 even in the operator norm as n goes to infinity. So again we use this shorthand an comma epsilon for the epsilon TSVD regularization of an. Okay, and this condition is equivalent to the existence of the more Penrose pseudo-inverse of A and an epsilon greater than 0. Spoiler, this is going to be the same epsilon as that one. Such that the pseudo-inverse of that TSVD regularized operator an converges to the pseudo-inverse of A. And again, that last convergence is great news because it means that the solutions of this least squares problem, which are computed by applying the pseudo-inverse of an epsilon to the right hand side bn, converge to the least squares solutions of this here, which is computed by applying the pseudo-inverse of a to the right hand side. So it's good to have the convergence of these pseudo-inverses here, just like we mentioned here. Okay, excellent. And now just for completeness, this very long statement here also has a name, but that name is actually not much shorter than the statement itself. One says that the sequence AN is stably regularizable, but I'm sure you don't complain if we abbreviate that phrase a little bit, maybe like that. Right, that's the new Polski theorem.